Here's sample test 4, problem number 2. The 20 ohm square loop at left is placed in a uniform 0.2 Tesla magnetic field directed perpendicular to the plane of the loop into the page. The square loop is then reshaped into a circle with the same total length. If the process takes 0.3 seconds, what is the average current generated in the loop? Alright, so we're going to reshape this square into a circle. It's all made of wire, so the perimeter is going to remain the same. So our original length is 8 meters. And our original area, initial area, will be 2 squared, which would be 4 square meters. And then we're going to reshape this thing into a circle of radius r. Our circumference of that circle, 2 pi r, will still be 8 meters. Perimeter will still be 8. So r is going to be equal to 8 divided by 2 pi, which will be 4 divided by pi. And hence our final area, which is pi r squared, is going to be pi times 4 divided by pi squared, which would be 16 pi over pi squared, which is going to be 16 divided by pi, which is 5.09 meters squared. So our change in area, which is our final area minus our initial area, is going to be 5.09 minus 4, or 1.09 square meters. Good to know. Our average induced voltage, our average induced EMF, is going to be the absolute value of negative change in flux over change in time times the number of turns. Number of turns will be a positive value, so this is going to be N times the change of our field times our area over the change in time, but the field is going to be constant, and so this is going to be equal to the number of turns times the field times the absolute value of our change in area over our change in time. Should be the absolute value. So we have, this is 1 for the number of turns. Our field is 0.2 Tesla. Our change in area is 1.09 square meters. And our change in time is 0.3 seconds. So this is going to come out to 0.729 volts. That is our change in voltage. We want to find the average current. Our average current is going to be our change in voltage divided by the resistance. So 0.729 volts divided by 20 ohms is going to be 0.0364 amps. Or we could write that as 36.4 milliamps. So that will be the average current induced in this circuit, in this wire, as we change its shape in a magnetic field. What direction will that current flow? Well, as we change the shape with a magnetic field going into the page and our area increasing as we're doing that, we need to answer those 4 questions, those hierarchy of questions, to determine the direction of current. First question is, what is the direction of our original flux? Well, it's the same direction as our original magnetic field, and it's going into the page. So our original flux is into the page. Second question is, as we proceed through the problem, does that flux increase or decrease? Well, the area increases, so the flux is encompassing more lines, and so the flux is increasing as we proceed through this problem. Since the flux is increasing, third question is, what is nature's response to this? It wants to oppose that increase that's going into the page, and hence it wants an induced field that is out of the page. Our answer to 3 is going to be exactly opposite direction to our answer to 1 if our answer to 2 is increasing. And it'll be the same direction as 1 if our answer to 2 is decreasing. Since B induced is out of the page, by the right-hand rule, in order to create a field that's going out of the page, we need to curl our fingers counterclockwise. So I induced is counterclockwise through this circuit. So our induced current is going to go this way through the circuit, counterclockwise through the circuit to create a induced magnetic field that's coming out of the page, opposing the increase in flux that's going into the page. So 36.4 milliamps counterclockwise through this circuit.